Another foundational idea in computer systems is the notion of a process, and we've been talking about this a little bit, but we want to dive into it in a little bit more detail now. And that's going to lead us into a little discussion of exceptional control flow, which is used by the process mechanism and by other important things that take place under the hood. First thing to note is the difference between a program and a process. So first of all, when I think of a program, what we're referring to here specifically is really just something that's in a file. Obviously, the whole discipline of software engineering and software development is focused on writing programs, and that's a really important thing, obviously, for us. But at the end of that process, we're going to end up with some collection of bits stored in a file someplace that represents the instructions that the computer needs to do something. The fact that those are sitting out there on a disk in a collection of bits means that essentially a program is kind of a static, inert representation of what we want the program to actually be able to do when it's running, but it is not executing at the time that it's sitting there on disk. We've been alluding to the structure of the files that contain these executable programs. In that program file, there's going to be some header information that talks about what's there, how it's structured. There's going to be the code that we're actually providing in our sources, so main, and then some function here called sum, and there'll be a bunch of other pieces of assembly language or machine language, assembled assembly language in this file that represent our source code. We're also going to potentially have spots for static data, and then there's going to be some other information that's added to the file that has information about like debugging data and symbol table information and some of that kind of stuff that's used for various purposes when the program runs. But again, that program is just something in a file. Now when we actually execute this program, we're going to create in memory a process, and this is an operating system abstraction of a program that's now executing. So whereas the program itself is this inert thing out in a file, the process itself is the executable portions of the program and the data that's defined in advance, loaded into memory, and then given life by the fact that the operating system will be able to schedule this process to be run, and the actual code is going to get executed by the processor. The structure of a Unix process in memory follows this basic pattern. At the top of memory, so this is the high addresses and low addresses in this little illustration. Near the top of memory, as we've been talking about, is going to be the stack. So this is where all of the pushes and pops and stuff are going to go. And we know that the stack is going to grow down toward lower addresses. Below that is going to be where the heap is located. That's where the malloc operation is going to go to get memory that can be allocated dynamically at runtime. And the heap grows up toward higher memory. And it turns out that because we've got quite a lot of virtual memory space here between the bottom of the stack and the top of the heap, that the operating system will also tend to load shared libraries. So for example, the implementation of anything in the standard I/O library like printf or scanf or whatever, the code that's going to be available to perform those functions is going to be mapped by the kernel into an area of memory between the heap and the stack. At the very bottom of memory in the process is going to be a read-only segment. This is basically going to contain the code. So anything that got compiled into our executable file that's going to be run by the processor is going to be stored here near the bottom of the process space. The reason it's marked here as read-only has to do with the fact that we don't want anything to be able to change the content of our code after the program starts to run. We'd like this to remain fixed and not sort of change out from under us. So the kernel actually will mark this as a segment of memory that can't be written to. Right above that, if there's static data in our program, for example, here I've defined an integer array with 2 values in it and initialized it to have 1 and 2 in those 2 locations. If that's a statically declared array, it's just got to be there in memory when the program starts. And so what will happen is the compiler and the linker and whatnot will arrange to have that loaded into memory with this initial value already set up, so that when the code starts to run, it can make assumptions about the contents of this array already being present when it starts to execute. For most arrays and other variables, those are usually going to be local variables. They'll be allocated at runtime and initialized by our code. But if we have static data outside of any function, this will be the way that we actually give it an initial value if there is one. Okay, so that's the basic structure of how the program gets loaded out of a file and loaded into a process in memory so that it can be executed. And we're going to just use this sort of simplified cartoon of the process in memory. So here's our stack and our heap, these two guys, the data that's allocated statically, and then the code at the bottom of memory. And then I'm also going to have this little representation of the state of the CPU. And I mean to include both registers and any other information that's stored in the CPU necessary to execute the process. And we'll see that this plays an important role in keeping track of the current state of the process as it's being executed. The idea of a process is another one of these things that is hard to overstate the importance of in computing. Again, just to cement this idea in your thinking, a process is an instance of a running program. The program itself is just this inert thing that's out on disk someplace. It's going to be loaded into memory where it's going to become a process. So this is a very important idea in computer science, and it's important to keep our terminology straight here. We're not talking about a program, that's the inert thing on disk, or a processor, which is the CPU that's going to execute the process, but the process itself is a unique individual thing all on its own. There's going to be sort of two important things that we want to keep in mind as we're thinking about how processes work. One of them is kind of the logical control flow, right? The way that the program executes when it's leveraging that instruction set architecture of the underlying processor in memory. It's going to turn out that the process is going to seem like it has exclusive use of the CPU, and we'll see how we switch from one process to another without the process ever having guilty knowledge of the fact that it's sharing the CPU with a bunch of other processes. And the mechanism behind this is something that's part of the operating system kernel called context switching, and we're going to talk about that next. The other important aspect of a process is that it has its own private address space. So not only does the process appear to be the only thing that's running on the CPU at any given time, it also appears to have exclusive use of all of main memory, and that's provided by the abstraction of the virtual memory system. Let's just think about what we're talking about in terms of multiple processes running on a computer at the same time. Obviously, we're familiar with this idea that a particular machine is going to be running many processes simultaneously. So in the user space, we'll be running a bunch of applications, maybe a browser, an email client, an editor, a compiler, a game, a weather application, whatever it happens to be. There's going to be a bunch of applications that are running, each of which is some program executing inside of a process. There's also going to be other processes that are going to be running on the machine that are kind of the purview of the operating system. So things like the networking code and the I/O code and the devices that are controlled by the I/O code and so forth. So if you think about it relative to the picture of the process that we had before, at any given time, we have a whole variety of processes that are all running simultaneously, sort of, on the machine at any given time. Now, I've titled this slide Multiprocessing the Illusion. It's not really true necessarily that all of these processes are simultaneously going to be making forward progress. They're not going to be occupying a CPU at all times. But we're providing the abstraction, the process abstraction, gives that impression that that's what's taking place inside each of those processes. We can get a little bit of a view into these processes by just using some OS tools. So this is actually an old laptop of mine when I took this slide. The program that I'm running here is called HTOP. It's a more elaborate version of a simpler program called TOP, both of which kind of just show you what's going on the machine. The top portion of this output is some information about the utilization of each processor. I think this was actually a 4-core machine that was hyper-threaded, so it appears to have 8 cores. And this is just kind of the percentage utilization of those 8 cores. The amount of memory, the amount of swap space, just some statistics about tasks. But the body of this page is a listing of all of the processes, right? So you can see that Google Chrome is kind of a pig here. It's got a whole bunch of processes that are running. I've got some other utilities that are running. Here's the HTOP process itself is executing here and showing up in this list. This is called top because it shows at the top the most resource-intensive processes that are currently on the machine. So there's a bunch of processes on here, but we can see here that although this is an 8-way hyper-threaded processor, there's only 4 actual processor cores, but there's a bunch of processes, and they go way off the bottom of the screen here, that are actually loaded into memory that are being managed by the kernel, and some of them, up to 4 of them, can be running simultaneously because I've got 4 CPUs on this machine. Here's another view from a different type of machine. This is actually the ICS server. This was a virtual machine. I think at the time it only had 1 CPU associated with it. You can see the memory and the swap space. And now there's quite a different collection of things that are running on a server. You can see there's a process called init. We'll come back and talk about that a little bit later. There's some various daemon processes that are running communications and syslogging and security and physical devices and a whole variety of other things. You can see that most of the processes out here are owned by the root user or by the system logger. There's a couple that are owned by me. The htop process itself is out there. There's also here's the attack lab daemon that shows you the statistics for that particular lab assignment and so forth. At any rate, this also illustrates the notion that since there's just one physical actually it's a virtual CPU, but there's one CPU here, and there's a bunch of different processes that are out there that appear to be running simultaneously, but obviously they can't all be using that one processor at the same time. So here's a kind of a reality check on that. Now I'm going to assume here that we're just talking about one CPU. As was the case back here in this server case. Got one CPU, got a bunch of processes. So we could think of the processes as all kind of stacked up here in memory. And because there's only one CPU, only one of those processes can actually be actively executing at any given time. And what we'll see here is that the execution of the different processes is going to be interleaved. So the CPU is going to run one process for a little while, then run the next process for a little while, run the next process for a little while. And that gives the illusion from the outside to the user that all these processes are executing simultaneously, even though they're only running one at a time if we have this one CPU assumption. So what we'll see here is that although we have multiple processes in memory, only one of them, this guy here, is being associated with the execution state of the CPU. So the CPU, the registers, the condition codes, a variety of other kind of internal things that are going on in the CPU that make this work. All of those things are dedicated at this particular instance in time to this one process. And the rest of the processes are still in memory. And what I've shown here, again, this is just a really super simple version of this. Instead of the registers that are actively being used by the CPU to execute this process, when we switched away from these other processes, we're going to see that we'll have stored that CPU state in memory so that later on we can resume the execution of this process. Here's a little bit of a sequence of how that actually might work. So again, here's that process that's running. It's currently got the attention of the CPU, and these other processes are still in memory, but they're just not being executed. At some point, the kernel is going to decide that it's time to give some attention to one of these other processes. So because it's going to temporarily suspend execution of this process, the first thing it's going to do is take all the state information out of the CPU, like the registers and other things, and store that information in memory in an area associated with this process. It's not actually executing any of the user processes. It's just busying itself with ferreting away the state of the execution of this process into memory so that it can come back to it later. It's then going to choose another process. So we've got 4 processes here, illustrated here, and the CPU has chosen to run this process next. Now what it's going to do is, at this point, the registers that are still in the CPU are the ones that it just saved over here, which means that in order to resume execution of this process, we've got to switch over the contents of the CPU, basically the state of the processor, to use these register contents instead. So that's the next step. After choosing this process, we're going to grab the information that we saved about its state of execution previously and load that into the CPU. And that's what's referred to as a context switch. We're switching from the process context here to the process context here. At that point then, the process that we're switching to can start executing. And it's going to run for a while until the kernel decides that it's time to switch to a different process. Just kind of raises the question of when does the kernel decide to switch from process to process. A really common case is when a process is about to request some sort of long-running operation. So if this process that we started with had just made a request to get data from disk, we know that that's going to take a very, very long time compared to the execution of individual instructions. So because this process isn't going to be able to do anything of use until that long-running disk access operation completes, gives the kernel a chance to say, hey, this guy is about to go and twiddle its thumbs for quite a long while until that disk access is over. Let's go do something that's actually going to make some headway on another process. So it finds another process that's ready to run. In other words, a process that's not itself waiting for some kind of long-running disk or network operation, chooses that process and starts running it. If doing I/O, for example, was the only reason that we ever switched from process to process, what we would find is that some processes would get a lot more of the CPU than others. If they just didn't do a whole lot of disk I/O or network I/O and ran lots of CPU-intensive work, once they started running, the operating system would never get into the picture again and force that process to wait its turn for some other processes to run. So in addition to those kinds of I/O kinds of interruptions in the process execution, the kernel is also going to keep a timer that's going to give sort of a maximum amount of time for each process to run. So some fraction of a second after the beginning of the execution of a process, if it's still running along doing useful things, but other processes have had to wait too long, the timer will go off. The kernel will say, okay, that's enough for you. Let's choose another process that's also ready to go and run it for a while. And eventually we'll get back to that original process that's busying itself with non-I/O related stuff. Although we have this illusion of a concurrent set of processes, it's really not taking place that way. It's concurrent in the sense that the control flow sort of overlaps in time, but on a single CPU, again, this is important to keep in mind, we're just talking about a computer with one CPU, these things have to be sequentialized. If this is our timeline going left to right, and I've got three processes here, and what I'm indicating here with just these bars is kind of a span of time during which that process is executing. So some process A is executing, and this arrow ending to this line indicates that there's still work for process A to do, that it isn't terminating at that point. So process A runs for a while, and then in this kind of interstitial space between these processes, this is an indication of work being done by the kernel. So if process A had made an I/O request here, the kernel would have said, okay, let's schedule somebody else to run because process A is going to be sitting around for a while the disk turns around. Let's start running process B. And maybe process B, in this case, because I've shown this kind of square end on this line, I'm trying to suggest that that means that process B is done. So process B exits. There's no point in keeping a process slot open for it in the operating system. So when the process exits, the kernel wakes up again, gets into the action and says, okay, let's kill this guy off, and we'll start process C and let it run for a while. And it's going to say just time out at this point, at which point process A may have completed its I/O operation. Let's let process A run for a while. It runs to completion, and the kernel switches back to process C and lets it run to completion, for example. So it's a kind of a back and forth between the multiple processes and the kernel, which is going to orchestrate the behavior of which process is running and for how long, and which process gets to execute next, and so forth. Here's some terminology. When processes are both executing actively and schedulable by the kernel, we'd refer to those as concurrent processes, even though they're not actually running concurrently on just a single CPU. These are concurrent with one another, but for processes that never are going to be running in the same span of time, we'd refer to those as sequential processes. So this process is done before this process starts, which means that they're sequential. From the point of view of the user, right? This is where we get this notion of concurrency different from what's actually taking place on the processor. We've seen already that this is the real picture on a single processor. The control flow of each of these processes is going to be disjoint over time. They're going to switch from one to the other. But from the perspective of the user, because we're doing these process switches really fast and computers run pretty quickly now, it appears as if these things are running in parallel, right? That process A has been running this entire time, process C runs this entire time, process B is sandwiched in there somewhere in between. From the user's point of view, we don't really see that change over from process to process. It's kind of hidden as an abstraction from the user to give the illusion that the processes are all executing concurrently. Now, what's actually happening when we do this context switch, when we switch from one process to another? We're basically allowing the kernel to activate a process after deactivating another process. So the control flow of that single CPU, again, is the assumption that we're making just for simplification. The CPU is now going to turn its attention from one process to another. This is something that's performed by the kernel, and I've been using the word kernel without defining it for you, really. I think you have a general sense of what that might mean, but the kernel basically is sort of the core of the operating system. It's memory resident. It's always there in memory. It's basically responsible for controlling the execution of everything that's taking place on that computer. So it's part of the operating system. It's always in memory, and it does a whole bunch of different jobs, but one of the jobs it does is manage these processes, right? So it's responsible for deciding that a process is done with its slice of time and switching to another one, or receiving a request from a process to do disk I/O and making that process suspended until the I/O is complete, and so forth. It's important to note that the kernel is not a separate process. It's, again, a part of the operating system. So when the machine boots, part of the bootloading process is going to be to get the kernel code itself off of disk into memory. And once it's loaded into memory, it's going to stay there until the machine is halted or powered down. So it is not itself a process. It's responsible for the execution of all of the other processes on the machine. And pretty much everything else that's of interest that's running on the computer while it's executing is going to be a process that's distinct from the kernel. So again, thinking about context switching, here's that same picture from previously of the different processes and then the time that we get to interact with the kernel between process pieces executing. So let's kind of zoom out on that and just kind of focus on this one little section here that I've highlighted in gray. When we're running inside of our process, so process A, process B, process C, we're running user code. This is just an ordinary program that we compiled and stored on disk, and our shell brought it into memory and started executing it. So we're running user code at that point. When we get to where we need to do a context switch, so say process A again is requesting some disk I/O, we then switch into kernel code. So we're going to stop running code supplied by the user, and we're going to start running code that's part of that memory resident kernel part of the operating system. And the job of the kernel in this little interstitial space is to switch from one process to the next. And that's exactly what we're talking about when we say context switching or context switch. It's changing the focus of the processing from one process to another process during that little time period between processes executing in user code. Of course, we hardly ever have a single processor machine any longer. So when we have multiple CPU cores on a chip or multiple processors in a larger scale machine, we're going to still be sharing main memory, right? We know that the virtual address spaces of the different processes is going to be mapped into pages of physical memory. In some architectures, like the Intel Core series, we're also going to share some cache between cores, right? We had the L1 and the L2 and the L3, where the L3 was shared across cores. And each of those CPUs can actually be executing a separate process for real at the same time. That said, though, process switching is still going to be performed by the kernel. So the fact that you could have, say, 4 or 8 cores simultaneously executing 4 or 8 processes doesn't mean that all of those processes are going to be executable at any given time. Some of them might block on I/O. Some of them might reach the limit of the kernel switching timeout. And so the process is still going to be managed by the kernel. It's going to determine what's actually running on each of those multiple cores. But now we really do have physical concurrency. It's not just an abstraction that's being made by the kernel for the benefit of the user. We really are going to have multiple things happening simultaneously. So here's just a simple example with 2 active CPU cores. Both of these processes here are going to physically be running at the same time. We really do get concurrency now in any kind of a modern process. But again, if you think back to those photos of the top program showing the very large number of processors, and there were more than that than would fit on the slide, they're all active processes in memory. So there's going to be a whole lot more processes like this one that are in suspended animation, sort of waiting to be executed, than there are like this one that are actually scheduled on a particular core in the computer. The way that process management is actually implemented on a Unix system involves what's called exceptional control flow. And we'll see that this is an important idea in terms of process management, but it also is used for other purposes on the machine. Here's a super simple model for program execution. Over time, going down the page, we're going to have the process that starts up, and then we're going to tick through instructions in sequence in the program itself until it runs to completion, and then we're going to shut it down. Super simple. Now we know that the execution of a program isn't just going to be in this lockstep sequential fashion. Of course, we're going to be able to alter the flow of control. And so far, the only kinds of alterations to that program flow that we've discussed are things that are right built into our program. So jumps and branches, the call and the return statements and so forth allow us to alter flow of control in response to the state of the program. In addition, we also want to be able to respond to state changes in the system itself, so the surrounding runtime environment that the program is operating within. For example, we might have data arriving from the disk or from a network adapter. So in the examples we were talking about before, where process A was temporarily suspended while disk access occurred, we want process A to be able to be notified when that access has completed and then start running again. We might have exceptional conditions caused by invalid operations. If we try to divide by 0, the processor is going to freak out and say, hey, we got a bogus operation going on here. We need to do something about that. If you're working at a console in a terminal and you hit the Control-C character, that actually causes a signal to be sent to your program to tell it that it's supposed to stop running. Or if the timer expires, for example, in the system with an alarm call. So we have both program state changes and system state changes, and we want to be able to react to the latter as well as the former. So we need to have some mechanisms in place that implement that exceptional control flow. The low-level mechanism is something, as you won't be surprised to learn, just called an exception. So this is something that responds to a system event, and it turns out that in most cases it's kind of a combination of the hardware and the operating system that make that exception happen. So an obvious example of that is the case of the disk controller signaling back to the CPU that it's completed doing an I/O operation to disk. The hardware is the thing that carries that signal across to the CPU, and then that's going to cause some activity to take place in the kernel. So the kernel is going to get control at this point so that it can do the appropriate thing in response to that exceptional condition. Important to keep in mind that the kernel runs in what's called supervisor mode. So when you're inside the kernel code, and if you think back to those process switch diagrams, in between those little narrow dotted lines, we're executing kernel code. And that kernel code executes in a special mode of the processor called supervisor mode, which basically gives the kernel unrestricted access to any resource on the machine. That's not the case for our user code. That's going to run in user mode, which does have limited permissions, which makes sense in that it allows the operating system to prevent malicious user code from doing bad things on the CPU. Let's consider a simple model of this exceptional control flow and the exception handling associated with it. Here's an illustration of our application program again, cooking along, executing instructions, and at some point in the execution flow, we'll just call this current. So this is during the process of executing some assembly language instruction, some external event or exception takes place. And what's going to happen is that we're going to switch control from our user mode into supervisor mode to the kernel. The event takes place, the timer timing out, say, And then that triggers an exception, which is going to now move our control from whatever assembly language instruction was executing on our application to code in the operating system, in the kernel, referred to as an exception handler. So this is instructions that's in supervisor mode in the kernel itself that's set up to be able to deal with this type of an event, whatever that happens to be. So for a little while, the code is going to execute in the operating system, and it's going to deal with that event, and we'll see different kinds of events that it knows how to deal with. And at some point, it's going to potentially return control back to the application program that was interrupted by this event. So we'll show the flow of control is going back to one of two places, either this instruction that we were executing at the time, or conceivably the next instruction in the application program. And we'll see why we have both of those cases in a minute. And then the application program continues to execute. So we've got the app program running. We get an event that triggers an exception. That exception is going to be handled by code in the kernel in what's called an exception handler. When the exception handler is done, it may return back to the original program, either restarting the instruction that was executing at the time or going on and running the next one. Again, keep in mind that this is in user mode. This is restricted access. So the application program literally has no permissions to be able to deal with that exceptional event. It has no choice but to switch into supervisor mode, where the event will be dealt with, and then the user mode may be reactivated. There's two types of exceptions to keep in mind with respect to the way that the timing of the exception takes place. An asynchronous exception is something that happens within the normal flow of instruction execution in the application process. We'll see, for example, that when we want to make a call out into the file system, say to do a write call or a read call or an open call to open up a file, that takes place right in the normal flow of processing. The application wants to open a file. It doesn't have direct access to the disk subsystem, so it has to ask the kernel for help in doing that. That's going to happen synchronously in the regular flow of control of that application. It'll switch into kernel mode to carry out that disk operation, and then it'll eventually go back to user mode. The other type of timing in an exception is an asynchronous exception. So this is something that's coming from sort of outside. A timer went off, an I/O request was completed. Those are things that are going to come from outside of the main control flow and have to be dealt with asynchronously. As I mentioned before, there's several outcomes that could happen after running the exception code in the kernel. One is that we could return to the current instruction, so the instruction that was executing in the application code when the exception took place. We might, in some cases, return to the next instruction, and in some cases, we're just going to kill off that application program entirely. Simple examples of this, returning to the next instruction would be the case in a synchronous exception like requesting access to a disk sector. The application code is going to invoke a system call to ask the kernel to go read something off of disk, and the kernel at that point will suspend the execution of that application process so that it can go ahead and start the disk access. And when that disk access is completed and the process is restarted, the next instruction in the application code is going to be executed. On the other hand, if the exception occurred was, for example, a page fault in the virtual memory system, the exception will cause the kernel to go and load that page from disk, and then it will restart the instruction that caused the fault to allow it to access the memory at that location. And finally, if the program does something completely illegal, like dividing by 0, the kernel is going to cause the program to abort immediately. Here's a little summary table of several different types of exception that we'll talk about in a little more detail. And in each case, we're going to look at a typical cause for that exception. We're going to look at whether it's handled synchronously or asynchronously, and we're going to talk about what happens next. So this little table might just serve as a reference for you for later. The first type of exception is just called an interrupt. This is something that's external to the CPU. For example, when the network stack receives an inbound packet, it's going to cause a physical hardware interrupt to take place. There's going to be a physical pin on the chip, sometimes multiple pins, that allow an outside device to indicate to the processor, hey, something happened that you should pay attention to. Because it could happen at any moment, it's an asynchronous type of a request. And what will normally happen is the processor will allow the currently executing process to finish its current instruction. Then it'll suspend that process, go off and run the exception handler that, for example, is going to deal with the inbound network packet. And the next time that that process runs again, it will execute the next instruction in sequence. So this is something that the kernel is doing just to kind of do bookkeeping behind the scenes. A packet came in, it wants to deal with the fact that the packet's been received, so it goes and runs some code in the network stack, and then goes back to running user jobs. Other examples, the user hits the Control-C key. That's going to cause a signal to be sent to the process. That's also asynchronous. We've already talked about the packet arriving on the network adapter. Another example would be when the disk subsystem finishes loading contents from the drive into memory using the direct memory access technique, and then signals the processor that the disk access has completed. Second example, often called a trap. These are intentional instructions. So what I was mentioning before, where the user process, for example, wants to request the contents of a sector on disk, it's going to make a request to the operating system intentionally, synchronously, to say, hey, I want to go get the contents of this disk sector. The process will be then suspended because that's going to be a long-running operation. The kernel is going to issue the request to the disk controller to read something off of disk. And when that response comes back from the disk controller and this process is scheduled to run again, the kernel will arrange for that process to continue execution with the next instruction. So the synchronous instruction was the thing that caused the kernel trap, jump out to the kernel and do something to get these data off of disk. And because that's taking place in the logical flow of control in the application program, the logical thing to do is to run the next assembly instruction following that. Examples of this would be system calls, and we'll talk about this later. So things like reading and writing from files, or even running a breakpoint. When you're working inside of the debugger, when you set a breakpoint, it actually makes a little modification to the way that the code's interpreted and causes an exception that jumps back into the debugger. Third is a fault, like a page fault. So these are unintentional exceptions. We're trying to access memory that currently hasn't been loaded into physical memory from the virtual memory system, but you can possibly recover it. So it's synchronous in the sense that you are executing an assembly language instruction that's trying to access a location in the virtual memory space that isn't loaded into physical memory, which is going to cause the kernel to go and load that page in and then restart the current instruction. Because that was the one that was trying to access the memory. We want to sort of give it another shot to do that in order to read the value into the program and then allow it to continue execution. Page fault is the most common example of this. It's also possible that the application program may have tried to access memory for which it doesn't have permission, which would be called a protection fault, and that would be an example of an unrecoverable fault where the kernel would receive the notification that the process tried to access something outside of its valid memory space, and the kernel's response would be to just kill off the process. So when you see in a Unix machine, you get an error sometimes, say from a C program that says something like general protection fault. That's what's going on. Finally, we might have an abort condition that's usually unintentional and something that you can't recover from, and the inevitable consequence is going to be to stop the program's execution. So for example, if the program jumps to the wrong location in memory and finds an illegal instruction there, in other words, one that doesn't correspond to an actual instruction's coding in memory, or something crazy happens with memory, these are things that just can't be recovered from, and the process will just be killed off. How does the kernel figure out what code to run in the face of different exceptions? Turns out that it will maintain what's called an exception table. Each of the exceptions that can be encountered by the kernel is going to have associated with it some sort of a numeric value from 0 to fairly small numbers, and that's going to be used as an index into a table containing addresses. This is quite similar to the idea of a jump table. So the exception table is just an array of addresses that correspond to the location of code in the kernel that knows how to deal with a particular exception by that numeric index. So if exception number 1 is triggered, the kernel is going to look in the second entry of this table at index 1, fish out the address there, and jump to the code that's at that address to deal with that particular exception. Here's just a really abbreviated list of the things that we might find in an exception table. So at index 0 could be a divide by 0 error handler. In the case of a general protection fault that we talked about, might be at location 13. location for a page fault handler, and so forth. Notice here that at the end of this exception table, there's quite a lot of entries left available for the operating system to use. And these are going to either be interrupt handlers that deal with hardware interrupts, or traps that are calls into the kernel to do something on behalf of a user process. Here's a simple example of how a page fault might be handled. We know that most of the pages are not going to be loaded as the program starts to execute as a process. And as soon as we start accessing locations in virtual memory, that's going to cause some initial page faults that are going to load those things into physical memory so that the program can continue to execute. So in the case of this instruction, which might be assembled into something that's like this, a move long of the constant 13 into this particular address in virtual memory, the fact that that virtual address causes a page fault at the beginning of execution because nothing's been allocated in the page table. When we execute that instruction, it's going to trigger a page fault, which is an exceptional condition. The page fault itself will have some sort of an index number associated with it that's used to look up the address of the exception handler in the kernel, and that code is going to be executed next. And when that code is completed and the process is then again ready to run, the exception handler will arrange for the process to be restarted at that same instruction, giving this code an opportunity to access the location that's now been mapped into virtual memory. As a second example, let's think about what might happen when an application program wants to do a write to a file. We saw before that the exception table allocates quite a lot of space for traps that the operating system can use, so this is a list of some of the traps. And we want to focus on this trap number 1, the write system call. When we talk about a system call, what we mean is functionality that's implemented by the operating system that's made available to our programs to be able to use on our behalf. They're not available directly to our process because they're under the control of the operating system as a shared resource that can be used by all processes on the machine. Making a system call basically is lodging a request with the operating system to go do something on our behalf and then let us know after the fact that it's been completed. We need to be able to tell the operating system which system call we want it to execute, and that's going to be passed in the A register. So in the case of the write system call, that's system call number 1, and we're going to store a 1 into the A register. There's going to be additional parameters that are going to be used by many system calls, just like a regular function call. We're going to put those into registers using the same conventions that we observed for calling functions in our own code. And then there's also going to be a return value that comes back from the kernel that our program will find in the A register. Here's a simple example that uses the write system call. What it's going to do is iterate over all of the strings that are being passed in the argv array and just write them out to a file. And we'll just focus on this one simple write call right here. The first argument to write is the number of a file descriptor. That's kind of the under the hood representation inside our process of an open file. And in Unix, the first 3 file descriptors are always the standard input, standard output, and standard error devices, and they correspond to file descriptors 0, 1, and 2. So the 1 here basically says, let's send some output to the standard output device. And what we want to send is the second argument. In this case, it's just a string containing a blank. And we also have to tell it how many bytes that we want it to write, and it's just 1 in this case. Let's look at how this simple write instruction is implemented in terms of system calls. We can see first of all that we're making what looks like an ordinary function call to this location libc write. Well, libc is the standard C library, and write obviously is going to be code that is going to invoke the underlying system call. We saw before that we needed to set some things up to arrange to call that particular system call. So the 3 instructions prior to the call are responsible for setting the parameters that are going to be passed to the write function. Here's the argument list again, just to refresh your memory. We're going to put something in RDI, RSI, and RDX. So here's the writing to the DI register. We're sending in just the value 1, and again, that's the file descriptor for the standard output device. We're going to put in ESI, the second argument that's going to be used by write, the location of the characters that we want to have written. So this is just basically this pointer is a reference to that literal string. And then the third argument, which is going to go in RDX, is the length of that string. And because that's just 1 character long, we're going to say 1. Now this call is going to invoke something that's linked into our program called libcwrite. These are basically hooks that are part of the standard I/O library that know how to invoke those system calls. If we go look at the code for this, I've shown just two of the instructions. One of them is setting a value in the A register. I said before that the A register is going to contain the index of that particular system call from the exception table. So I'm putting a 1 in there to signal that I want to use the write system call. And then I'm running this instruction, syscall. This is an instruction that's doing quite a lot of stuff. In particular, it's switching from user mode to supervisor mode, and then it's going to cause this exceptional condition. It's going to cause this trap to execute. Inside the exception handler, it's going to figure out, hey, the user is asking for me to run the write system call, and it's going to call that code inside the kernel, which is written to expect these 3 arguments located in the usual registers where we pass arguments. And in kernel mode, that write call is going to execute to do the operation associated with writing this string of 1 character to standard output. When that's all done, the kernel is going to arrange for the process that was waiting on that write system call to complete to become runnable again. And when it's next scheduled on the processor, it's going to continue executing right after the invocation of this write function. It's important to keep in mind that what's actually in the standard C library when it's making a system call is really quite simple. All we're doing is setting up to pass parameters into the kernel. We're calling this little stub function that's going to set up the appropriate value in the A register for the underlying write call, and then we're running that thing as a system call, which traps out to the kernel and ultimately invokes the kernel's write function. Notice that we don't have to know in our code what the index is for that write system call. This is code that's come out of the standard C library, where the source code has the definitive definition of the various indices into that exception table that say table entry number 1 is the write call, store that in the A register, then trap out to the kernel, which is going to fish that value out of the A register, invoke the write function, and pass to it the parameters that you've already set up before you jumped into kernel mode.